Yeah, welcome everyone for this Pico-electrodynamics theory series, which is part of the Pico-electrodynamics theory network, where we are really trying to understand the electromagnetic phenomena at the atomistic level. Some of the unique phenomena related to the Pico-electrodynamics is the atomistic anomalous waves inside the material, new topological aspects, and the angular momentum of the gauge field of these charges. So as a part of this Pico-Seminar, we are trying to bring in both experimentalists and theorists working in many different areas, including the quantum optics, many-body physics, computational electrodynamics, and the density functional theory. So we had many excellent speakers in this series, and today we have Professor Gururaj Naik from Rice University. Now, Professor Jacob will introduce him. Thank you.
Thank you so much, Satvik. Really appreciate it. Today, it's my pleasure to invite and welcome Professor Gururaj Naik, a very good friend of mine. We have worked together on many problems over the years, and I'm looking forward to his talk. I'll tell you a little bit about him. So he is currently an associate professor at the Electrical and Computer Engineering Department at Rice University. He received an ME from the Indian Institute of Science in India, where he won a gold medal. Then he did his PhD with the groups of Professor Shalaev and Professor Boltaseva, where he was really the pioneer and kind of one of the first people to start all this interesting things on the plasmonic materials and nanophotonic applications with Professor Shalaev and Professor Boltaseva's groups. And his research has been very widely kind of appreciated both in the MRS community as well as the OSA and IEEE photonics communities. So he's worked as a postdoctoral scholar in Stanford for a few years after his PhD, and then he joined Rice University in 2016, and he has been there since then. So today he's going to talk about a kind of very interesting topic of putting together nonlinear and non-local optical response in quantum materials. So we are looking forward to the talk, and thank you, Guru, for accepting our invitation. And we look forward to the talk as well as the discussion.
Thank you very much, both Zubin and Satvik. It's a pleasure to be here and also see all the familiar faces and people that I have interacted and learned from in the past. So thank you for this opportunity. So let me begin by first sharing screens so that we can learn a little bit more about what my group has been pursuing recently with respect to quantum materials. So today I'll talk about only two aspects of optical response in quantum materials, just nonlinearity and non-locality. There are many more. And the point of this talk is to simply highlight that there is a non-trivial light-matter interaction regime with quantum materials, and there is a lot to be done to understand it. So first, just to highlight what is how light interacts with matter, just generally. When I say light, I'm still talking about optical frequencies, so where electronic response is the most dominant form. And in this case, in conventional materials, these are simply individual electrons interacting with light, and which gives rise to their optical response. So that's what we know for metals, semiconductors, etc. The response is fast and usually also small. So when I say small, it's not that strong response. It's coming from just single electrons and the states involved in this response. But when we talk about quantum materials are generally strongly correlated materials, this is not the situation. So the electrons are no longer individual, but they all are together. They are connected to each other. So the many body effects show up. So it's like a jelly of all these electrons. So when light interacts with it, then it triggers a wave or a response from this jelly of these electrons. And that's where the response is fundamentally different from conventional material. So strongly correlated materials thereby exhibit complex light-matter interaction. And do we understand it, or what is really the hallmark of this response? So that's what I want to explore in or discuss in this particular talk. So first, let's understand a little bit about quantum materials, just to get this feel of why this is complex. So quantum materials, first of all, they're interesting, or the strong correlations happen, or many body effects happen because of something that's unique to quantum materials. So if you look at the way quantum materials or electrons in them can be described, so a popular model is just this Hubbard model. There are many versions of it, Hubbard, Holstein model, etc. But let's begin with simply this Hubbard model. So where there is this first term in this equation, which simply talks about how electrons jump from one side to another, just delocalization of electrons that we're familiar with any tight binding model. So that's not surprising. But what is unique to them is the second term, which is the on-site potential or just the electron-electron interaction that can happen in these materials. So U is basically a parameter that captures the strength of this interaction. And if we plot all the materials conventional to the quantum materials here as a function of this U divided by D, so which is the on-site interaction strength divided by the hopping interaction strength, then if we see that all the conventional materials like semiconductors, metals, they all simply fall in this region where U is very small compared to D. So it's basically just delocalization of electrons. We know how to solve them. But in the case of quantum materials, it's U that is stronger or comparable to D or even stronger, where we see many body effects to dominate. And because of that, these quantum materials have many different phases. So there are microscopic phenomena that come from this many body effects, and many of them are competing with each other. And that leads to phase transitions or many different phases to show up in this quantum materials. So just an example of here, a cuprate phase diagram where we see here the semiconducting phase or pseudo gap phase, many different ones that we are aware of, antiferromagnetic, etc. So similarly, of course, there are a class of chalcogenides, 2D materials or quasi-2D materials, which also, in fact, exhibit such kind of strong correlations and interesting phase transitions. So here is an example from 1T tantalum selenide telluride alloy system, so which also shows this interesting phase diagram. Okay, so we are interested in such kind of materials and particularly look at the charge density wave phenomena in this phenomenon happening in these materials. Okay, that's what I'll talk about in this class. So in the charge density wave materials, again, there is the same Hubbard model that works. There's also the electron phonon coupling that needs to be included here, without which there are no charge density waves. So charge density waves, simply said, are nothing but just the charges which are all interacting with each other. So through Coulomb interaction, it's not like individual charge, but everything is together making a wave. So in fact, the history of it started long back. It was predicted in 1955 by Perels. So where he said 1D metal simply cannot exist by saying that if we had a 1D chain of these atoms, then the atoms can simply undergo a slight lattice distortion such that they pair up, and that opens a band gap. So which makes them semiconducting, and their energy, overall energy, reduces. So that's the most stable form. So what he said was, now the atoms which possess charge can simply undergo a slight lattice distortion, slightest possible still, to open a band gap and then reorganize themselves. Right. So this was predicted that then, of course, it was observed in many materials since then. And tantalum disulfide is one of the candidates here that we will focus on, which also shows this kind of charge density wave behavior. This is a 2D material, so which means the charge density waves are 2D sheets of this charges. And the lattice reorganization has been quite nicely studied in 1960s, quite elaborately, and then recently again. Okay, so why are these charge density waves interesting? So charge density waves, without any of this strong correlations, we would simply have their energy landscape to look like just a single cup with one minimum, global minimum. So that's where the system would reside. Then you'd simply have metallic phase. So nothing really special about it. But in the case of this charge density waves, or generally this strong correlation, we'll see that the energy landscape is no longer the simple cup, but actually hat shape. So which means there exists a minimum, not at the center, but actually at some other distance away from the center in this phase space. And that's where the charge density wave phenomena happens. It's a wave because, of course, it can pick any phase on this circle. They all have the same energy, minimum energy with them. So you can assign an order parameter because of the energy landscape that shows up in this. So why tantalum disulfide? So tantalum, I'm an experimentalist, so we need to think about how can I make this material, how can I probe this, etc. That's what really led me to tantalum disulfide. So one of the coolest part about tantalum disulfide, first of all, it's 2D, so which means I can pick a crystalline 2D material and then simply exfoliate layers from this, multiple layers. I'm not talking about single layers, but actually hundreds of layers, and still get a crystalline patch of this material. So that's easy. I can put it on any substrate that I wish, and that's very easy, convenient for experiments. So that's one of the things. And the second thing is a lot of the strong correlations often come at low temperatures, where the phonon interaction or the temperature-induced interactions are small. And that's where we see, for example, superconductivity, antiferromagnetism, etc. But in the case of tantalum disulfide, we see this charge interaction, strong charge density wave interaction happening at room temperature. So in fact, it supports two modes. It has both Mott gap and charge gap. And the Mott gap vanishes somewhere about 180 Kelvin. And then beyond that, even at room temperature, there is still a charge gap. And the charge gap vanishes somewhere about 80 degrees centigrade. So at room temperature, there is a strong charge gap that exists in this material. So it also shows peculiar phase formation, so which is there are domains where the material has condensed into this charge density waves. So the charge density waves, in fact, show up in this material as this David star formation. So where 13 tantalum atoms slightly dislocate from their lattice centers, just fraction of a picometer, to host exactly one charge in them. And these David stars interact with each other, making a charge density wave domain. At room temperature, this material has many of these domains, and then in between these domains, we see that there are metallic regions where conduction can happen. So this is a metal at room temperature. So if you look at the resistivity as a function of temperature, it's at very low temperatures, it's an insulator because of the Mott gap that shows up. But at about 180 Kelvin, the Mott gap goes away and then the resistance falls down. It's simply just a charge gap material. But as we keep increasing temperature, this domains become smaller and smaller, leading to larger and larger metallic conductivity in this. So that modulates the resistivity further. And then at about 80 degrees centigrade, the nearly commensurate charge density wave phase vanishes and the charge gap goes away. And then there is only incommensurate charge density wave phase where everything is metallic. So those are the interesting three phases that this material exhibits. So because of room temperature charge density wave interaction, this material has caught a lot of attention in the recent days. So, and it has been shown to exhibit tunable electronic properties or electrical properties. Here, for example, just with pressure, they have shown that you can get superconductivity to come up in this material. So superconductivity and charge density waves, they compete. They come from the same interactions and they compete. In just tantalum disulfide, superconductivity doesn't show up only because charge density waves are dominant. But pressure can suppress charge density wave interaction and bring superconductivity up. And similarly, just by changing thickness, it's been shown you can bring again superconductivity or suppress charge interaction, charge ordering. And similarly, electrical bias, even a vertical field effect bias like a gate bias, or even in-plane electrical bias, both have been shown to tune this electronic properties of this material. So the question that we had was, what about optical properties? And we couldn't really find any material that talks about dielectric constants. There were many which did high intense lasers and then, for example, time domain reflectivity measurements. but none of them really talked about how just generally the linear response function depends on any of these phases that exist in tantalum disulfide. So we wanted to try that. So what we did, in fact, is to, as I mentioned, to exfoliate a thin, about 80 nanometer, 20 to 80 nanometers. So we have different thickness samples, just that crystalline film, and then put it on a substrate and then measure optical properties. Even before we did electrical properties, just to prove ourselves that there is this charge density wave behavior. And a typical way to prove that is to show that there is a nonlinear DC conductivity in this material, and that has a particular form, which in fact comes from theory of how this charge density waves can be trapped in defects, and you have unpinning of this charge density waves at a threshold electric field called ET. So we see a very similar behavior as theory predicts, which is an indirect proof that charge density waves exist at room temperature in this material. Okay, so then we wanted to see how optical properties exhibit or change. So what we did was to put this thin film of this tantalum disulfide under a microscope. And we have, in fact, a Fourier plane imaging microscope, so which means we can take angle resolved reflectance and transmittance from small area samples. So from that, we can extract the optical constants. So we did extract optical constants at very low illumination intensity. So all I'm talking about is incoherent white light illumination, no coherent illumination like laser illumination here, just white light from a tungsten halogen lamp. So here the intensity was about 10 milliwatt per centimeter squared, and we extract the optical constants. It's a uniaxial material, so in the plane I have one particular permittivity and out of plane another. So I have both of them, the real and imaginary parts, shown here. It's not really very interesting because it's just an absorbing dielectric. Nothing special, at least at low intensities. But what is special is the intensity dependence of these optical constants. So if we take two different white light intensities, so low intensity here about 10 milliwatt per centimeter squared, high intensity about 1000 milliwatt per centimeter squared, and then this is normal incidence case, I don't see any change in reflectance. But I go to oblique incidence, I see that the reflectance changes. So that was very surprising. And since it changes only in oblique incidence, and not in normal incidence, our idea was that only this epsilon out of plane or epsilon C axis is sensitive to intensity, not epsilon in plane, which is the ordinary permittivity. So we basically extract this out of plane permittivity as a function of illumination intensity. So here we have the illumination intensity, all incoherent white light illumination from 10 milliwatt per centimeter squared to 1000. And just to give you an idea, 100 milliwatt per centimeter squared is one sun intensity. So that's ambient sunlight. Right? So we are talking about simply ambient light changing optical constants by this much. So which was quite exciting, interesting. And we wanted to find out why this happens, how fast it happens, all those things. So we did some time domain measurements as well. So first of all, what we found out was this is the time constants are in the order of microsecond, actually sub-microsecond, just hundreds of nanoseconds. It's not very fast, but it's still sub-microsecond regime. And another thing that we saw was this time constants do not change. They're actually, when this time domain measurements were all done with laser. This is not white light. So we also had some heating of the sample. So we had two time constants. So the thermal time constant and another we think is electronic time constant. And we saw that they don't show any power dependence, so which is good. So we can think of a simple thermal model for our material. So that's what we found out. And then we wanted to find out for this white light case, what are the possible mechanisms for optical tunability? So is it free electron generation? And that simply ruled out because we have so low intensity of illumination that you cannot generate so many electrons to change optical constants by unity order. And what about nonlinear optics? We did try looking at some higher harmonic generation. We didn't see any such possibility. Again, our intensities are very low. And what about light-induced thermo-optic effect? Just light causes heating, and heating changes refractive index. So that is probably the most serious contender here. And then we did build some thermal model. We don't have, of course, thermal conductivity of a lot of things here, but we gave some freedom here and then chose the most lenient thermal resistances so that we can expect the or find out what is the maximum possible temperature rise in our sample. And even with the most lenient parameters here, we got something like about 0.5 degrees centigrade as a maximum temperature change in our sample, which is still too small to expect unity order index change. So the remaining one is simply to suspect that it's something to do with CDW. So about the same time, there were two papers in arXiv which talked about a phenomenon. They said how the CDW domains stack on top of each other. So depending on how they stack, there can be very different electronic properties. That's what these papers said. So for example, here I have, let's consider these two layers. So this is layer 1 and upper layer. So these are two charge density domains there, the David stars. If they're stacking staggered, not on top of each other, but staggered, then if we look at their C-axis electronic property, then the density of states goes to 0 at Fermi level. So it is semiconducting. On the other hand, if the stacking were all on top of each other, then we can have the density of states non-zero at the Fermi level. So which means it's metallic. So this paper suggested that just by changing the stacking of the CDW domains, the material can exhibit semiconducting or metallic electronic properties in the C-axis. So we thought maybe that's what is changing the optical properties. Okay, so we hypothesized saying that at room temperature, probably there exists two different stacking configurations. So here, the bottom layer domains are all shown in gray, and the top layer gray domains are all shown in color. And we have two different stacking here. So one is blue stacking, which is staggered, and the red one is center to center stacking on top of each other. So we said at room temperature, both these stacking domains coexist, and just that the ground state one, which is the blue stacking, is more preferred and they're bigger domains. When we turn light on, then somehow the domains shrink, the blue domains shrink, letting the red domains to grow. And that's what changes the optical properties. So this was our hypothesis. Okay. To test this, what we did is just simply build a 3-level model. So where we have this upper level stacking and lower levels ground state stacking shown here. And then we have light causing all the transitions. The key time constant is this one, which we measure from experiments. And then using that, we can predict what fraction of CDW domains exist in this higher level stacking. And then we use, in fact, a Maxwell-Garnet effective medium theory to predict what should be the optical constants at any of these intensities. And then we see how they match with experiments. And the matching is quite remarkably good. And this has no, in fact, free fitting parameters. We're really surprised that it actually does so well. And about the same time, there are also a few other papers that came up which did TEM studies and X-ray diffraction studies to show that light indeed changes the stacking of CDW domains. So that was quite interesting to say that, okay, there is some intensity-dependent optical response or nonlinear optical response, simply that comes from how this CDW domains reorganize or stack on top of each other. So now if this was the case, then there must be some dependence on temperature, because temperature changes the domain size. So what if we reduce temperature? What do we see in terms of this tunability or nonlinear optical properties? So what we saw was here again reflectance at one particular wavelength plotted as a function of temperature of the sample. So at room temperature, we see some. As we reduce temperature, the reflectance change goes up. But as we go to further lower temperatures, like go to commensurate phase, so which is where the whole layer is condensed into a CDW domain, we still see tuning, but it's small. We still see tuning. So that was surprising. So what we thought was, so if we simply look at the Coulomb energy difference between the two stacking as a function of domain size, so that is number of stars per domain. So this keeps growing. So the energy difference between the two stacking simply grows with the domain size. So if the domain size in the limit goes to infinity, we should see a huge energy cost for switching from one stacking to another. So which means in the commensurate phase, that is at very low temperatures, we shouldn't be seeing any appreciable change in reflectance, because that's not energetically favorable. But we still see change in reflectance. So that's one thing that was surprising. The other thing that we saw was there was a maximum which was not anywhere close to any of the phase transition temperatures. So which we thought is simply a competition between how many of them change, and then how easy is it to change. So as the domains grow bigger, the energy cost is high, so there is less probability of change. But when they change, because a bigger chunk of the fraction of the sample changes, there is also a bigger optical response. So this two opposing factors give somewhere in between this peak in tunability or nonlinear effect. So that's what we concluded from this particular work. We also characterize this time constant. So how fast these changes happen as a function of temperature. So as we reduce temperature, just pick one curve. So there are two curves here. So one for light on, one for light off. There is a hysteresis because of thermal or photothermal effects. So that's why we have these two curves slightly displaced, but they show qualitatively the same behavior. So as we reduce temperature, the time constants decrease. So they become faster and faster. But as we approach this phase transition point, so which is about 180 Kelvin, where the Mott gap shows up. So we see that the time constants go up again. They shoot up to a very high number, and they again drop as we reduce the temperature further. So this was quite interesting. We didn't really know how to explain this phenomenon. So what we started our thought was, let's assume that there is an energy cost or two different stacking here. There can be a transition between them through an energy barrier. So just like how nucleation theory assumes that there are two different states, and then there is a barrier that it has to go through for going from one to another. So if we assume this kind of our nucleation theory model, then we could explain this behavior. So in fact, what we did was, let's assume that the rate of CDW domain switching from A to B versus B to A, they can be written down simply by this nucleation in a nucleation rate, which we know from nucleation theory, and then just write down the rate equations in steady state. And if we do that, we can reproduce exactly the time constants. I think I missed this. The behavior, the time constants must behave exactly the way we saw. First, they drop down, and then at the phase transition temperature, they go up, and then again it comes down. So we could think of this, but again, there are a few details that I didn't mention. So for example, how this energy of a photon that is absorbed by the CDW domain, how it is shared between the domain, the stars in the domain. Do the stars actually completely break and then reform again, or do they reorganize? So those are some of the details that I skipped. Maybe I can take them up in the discussion part. Okay. So all of this, in fact, led us to this model, so which is that there exists both the two kinds of stacking picture here, the domains. They coexist at any temperature, whether it's commensurate phase or in nearly commensurate phase. All of them coexist. So meaning different stacking configurations coexist on this, and there are domain boundaries, so which are shown by this yellow stars. And they really decide in how they take away the energy from the photon that shines on this material, and then eventually redistributes or reorganizes the fraction of this different stacking domains. So that's the final model that we came up with, which so far explains everything that we have seen. Okay, so not just in the case of light, but we can also see this tunability with an electrical bias. We simply apply an in-plane DC bias. So here is our tantalum disulfide film, and then we have gold contacts which are underneath this film. And these are 4 contacts here, and we apply bias across 2 of them and measure current through the other 2. And what we see is as we increase the bias here, the bias current, so here from 0.01 milliamp for this green curve to about 1 milliamp for the red curve, this is for the DC case, we do see that the angle resolved reflectance shows a change. And similarly with the AC bias at 1 megahertz, we do see a similar change in reflectance. And this is quite a lot of change in reflectance for this 20 nanometer thin film. So again, I think I haven't discussed all the things here, but what we come up in this analysis, we also have a few other simple, just electrical resistance measurements as a function of illumination intensity, etc. But the summary of all our analysis is shown here. So which is with an electrical bias, what happens is the ground state stacking is more preferred. And just the same thing that we had in the previous case. So we have both of these blue and red stacking domains to show up in our material. But as we now bias this, the blue domains increase in size and red domains shrink in size. So that's contrary to how it happened with light. So electrical bias pushes this way, light pushes the other way. So that's what we came up with. And why does this happen? In fact, we can think of this as we apply an electrical bias, the charge density wave domains simply are shook. So it's as if like we have this, you can think of this as maybe eggs in this egg holder, and then some of them are dislocated. Then now you start shaking them, you have a better chance of putting all these eggs in the respective places. Right? So which prefers the ground state stacking better than the upper state stacking. And that's why we see this behavior. So we came up with a model to explain all of this. Okay, at this moment, I think I'll switch gear on to talking about non-locality just quickly. I see that I have already exceeded my time probably. So let me be quick in explaining what we have been doing with non-locality. We don't have, of course, a lot of momentum in understanding non-locality yet, but let me introduce where we have started. So I mentioned about Maxwell-Garnet effective medium theory. So what we do is we assume that there are two different epsilons for this two different stacking or two different permittivity functions. And then we assume this Maxwell-Garnet equation, and then for a given fill fraction, find out what is this effective epsilon. So that's how we come up with this effective epsilon or effective dielectric permittivity. Okay, so this fit looks good. Of course, this is for just normal incidence or one particular angle. But what happens is as we change the angle of incidence from normal, let's say normal, it fits really well. Then for the same optical constants, if we find out what to expect at 40-degree angle of incidence, we don't see a good agreement between experiments and theory. So it's really difficult to find one optical constant, local optical constant, that fits really well for all angles of incidence. And that's where we think local dielectric function is not the right model for our material. So why? So we have two different stacking, and this material is clearly inhomogeneous. And if this inhomogeneity is on the order of wavelength, we should expect non-local effects. Of course, just charge density waves themselves behave like hydrodynamic behavior, and there is non-locality, which some papers have already talked about, and we're still not there to probe them, but clearly the stacking is one of them, which should be easy to probe. So that's where we began. And this is my student Dingus here, who can probably talk more in the discussion session, but how he has started working on this problem is to simply assume that there are two different polarizabilities for two different stacking. So here two alpha 1 and alpha 2 are their polarizabilities. Then we assume that they're at least to start with in a nice periodic lattice, but eventually we extend this model to randomization, size variations, all of them. Okay, so the way we handle this is self-consistent solution to susceptibility. You solve for local fields and global fields. And so applied field is E0, and then local field is E1 in domain 1 and E2 in domain 2. So we need to solve for the fields in these domains and then get the effective susceptibility, which should be dependent on the angle of incidence, or K of the incident light. So that's where we are currently working on. We're still benchmarking our model. And I don't have the results applied to tantalum disulfide yet, but that's where we are heading towards. So with that, I would like to conclude this part of my talk. Hopefully I have convinced you that the quantum materials do show very interesting optical properties, optical response, where our conventional treatment of materials is not sufficient. We need to handle many body effects, the competition between microscopic processes, and how light can tip balance between some of this competition, and thereby give rise to nonlinear and non-local optical response. So I would like to thank, of course, my students who enabled this research, and especially I think Ding here, who is currently working on this problem, and Wei Jian Li, who graduated, who started the whole work on quantum materials and their optical properties. And thank you all for this opportunity and listening to me.
Great. Thank you, Guru, for this really spectacular talk. And I should say welcome to Vlad and Sasha. I see that they joined a little late. Thank you so much for joining. We do have the recording of the entire talk, so we can go back and look at that. So what we would like to do now is kind of start the informal discussion part of the talk. And we would love for Vlad and Sasha to stay as well for the discussions and maybe go over the slides again. We will thank Guru and Satwik once again, and we'll kind of wrap up the kind of live streaming part of the talk, and then we can just have an informal discussion on all the points and talk about this super interesting material. So thanks again, Guru and Satwik.